we go. Okay, 6.2 trig proofs. It's going to be like what we did in 6.1, except I think a little bit easier because we're going to have a clear target, whereas in 6.1 we were just kind of simplifying. So I think I've mentioned this quote before, but this is one of my favorite math quotes. W.S. Anglin. I believe math education is to get you to think. That's its sole purpose. But you know, to do that, you have to care, right? And then when you persist and you think all the way through from start to finish, you develop sisu. And this one quote kind of embodies all of that. W.S. Anglin said, mathematics is not a careful march down a well-cleared highway, but rather a journey into a strange wilderness where the explorers often get lost. And you can stop right there. That kind of sums it up. Rigor should be a signal to the historian that the maps have been made, and the real explorers like y'all have gone elsewhere. So we're trailblazers. We're bushwhacking. Okay. Let me show you what we're doing here. We'll just jump into example one. The instructions are going to be to prove. So you know this is going to be an identity. Okay, the left side is the same as the right side. They're mathematical synonyms. You can replace one with the other without a loss of generality. So to prove it, we draw a line down the middle. Okay, that's your first step. Now the first strategy is it doesn't matter what side you start on, as long as you manipulate both sides independently, you can't cross-contaminate. When one side looks like the other, you're done. But as I might have mentioned in 6.1, you're going to want to start on the side that has more information or looks more complicated because it is easier to tear down than it is to build up, right? I think I mentioned when I built homes, it took a lot of people with different skill sets, a lot of time to put together those things to construct the home. But when I had that one house burned down in Brown Oaks, man, we had it destroyed and demolished in one day. That was after the fire. So it's easier to tear down than to build up. So which side looks like it's more complicated or has more information, left or the right? The left. Okay, I would agree for a couple of reasons, right? It has two trig terms, whereas the right side has only one trig term. And then another reason is it has a larger exponent. So when you have an exponent that's a larger degree, it basically contains more information. All right, so I'm going to start on the left side, and I want to make the left side look like the right side. Well, it's already in terms of sine and cosine. We know that that was a strategy back in the day. I want to make the left side look like the right side. So here's what I noticed. I noticed that the right side now becomes my target because I'm starting on the left side. And I also noticed that the right side doesn't have any signs in it. It's exclusively in terms of cosine. So my goal is to try and somehow get rid of the sine to the fourth and write it in terms of cosine. Now, the other thing I noticed is I need to get the degrees down from 4 to 2. One of the ways we have to do that, since there are no identities, like the Pythagorean identities don't work on fourth powers, one of the strategies is to factor, right?
We can factor out sine of x into 1 minus cosine of x.
No, that doesn't work, right? It has to work only if it's squared, right? So 1 minus cosine to the fourth of x is not equal to sine to the fourth of x. That does not work. That only works if it's squared. Now, here's what you could do if you wanted to. You could call sine to the fourth sine squared of x quantity squared, right? So I'll do this a couple of ways. So that's one way to do it. Now, notice what I did there is I just wrote sine squared squared, and I wrote it two different ways. I wrote the expanded version with the parentheses, but I kept the sine squared and condensed version, right? So Brady had the idea of using the Pythagorean identity, but it has to be squared. So now on the inside and the inside only, okay, I do see a sine squared. So now, Brady, on the inside and the inside only, I can replace sine squared with what? No, not cosine squared minus 1. 1 minus cosine squared of x. Okay, so that had the effect of putting everything in terms of cosine, which is good. So now what can I do? Is there any obvious math that I can do now that I created by substituting a single term with a two-term dude? Something minus something quantity squared. Can I expand it out? Yeah. What would inform me to do that? Well, obvious math, right? But look at the right side. It's not factored. It's completely expanded. So you remember how we square a binomial? We square, multiply, double square. Square, multiply, double square. So when I square the first term, I get 1. I multiply these two together and get negative cosine squared. If I double it, I get negative 2 cosine squared. That's good. And then I square the last. What's negative cosine squared times negative cosine squared? Positive cosine to the 4th of x. So that's what happens when I square, multiply, double square. And then I bring down the minus cosine to the 4th. And now, is anything good happening? If you look at your right side, you're like, man, I'm really close. What happens with these two like terms that are opposite signs? They cancel out, and I'm left with 1 minus 2 cosine squared of x. Okay, if you want, the process is the product. If you want to draw like a little line through there, as long as I can still see what's underneath there, that's fine. You don't have to put plus 0 here. I mean, technically, it would be preferred if you did that. But I'm not going to make you do that. If those cancel and I can see they cancel, you can go straight to that. Now, does the left side look like the right side? It does. So now you can write QED, or you can sign off with something like Ole. You can sign your name, make it fun. This is where you get to be original. So there you go. We were able to use the Pythagorean identity. It just had to be squared. So we didn't really factor there. We actually did the opposite of factor and we expanded out. I was going to do it a different way until Brady kind of inspired us to go this way. Is that the only way to do it? No. So let's look at another way. Okay. If we could do things more than one way, especially while we're learning, all it does is it informs us of different strategies, right? And the more experience we have in different situations, and the more options we have, the better we become at solving these. What I would notice right away is that I could factor sine to the 4th minus cosine to the 4th. That's a difference of squares. Y'all see that? It doesn't always have to be boring powers of 2. As long as those are even exponents, they're perfect squares because you can write it as something to the 2nd power. So we know that the difference of squares factors into the product of 2 whatchagates? Conjugates. So what would be the square root of sine to the 4th? Sine squared of x would be the square root of sine to the 4th. And cosine squared of x is the square root of cosine to the 4th. So we know that the conjugates are going to only differ by the middle sign, right? So you can write sine squared, cosine squared, cosine squared. And one of them is plus and one of them is minus, yes? Yeah. Okay, so that's one way to go to start off. Now, what do you notice about sine squared plus cosine squared? In the front there, that first factor. That's equal to what? That's equal to 1 by Papa Pid, right? Now, you do want to show that that's equal to 1. That's a little bit different than having 2 things that are already there and cancel. If you're ever doing a trig substitution, you need to show me the substitution. So I know they just didn't fall off the face of the earth. And now on the inside, I'm making progress because I got the degrees down from a 4 to a 2, but I still have an unwanted sine squared. So now would be the time also in this next one to actually replace sine squared with what? 1 minus cosine squared. Yeah. So I did 2 things on that line. I used Papa Pid, and then I used Papa Pid again, but in a different version. Now, 1 times anything is itself, and now I can combine these 2 like terms, yes? Minus cosine squared is minus 2 cosine squared of x. And I got it. It's the same on both sides again. So which side is correct? Or which version is correct? Both of them. Is one preferred over the other? Yeah, the one that we did on the right has 1 fewer lines of writing. So, the shorter, the better. Now, notice I started on the left side and I stayed on the left side. The ideal way to do these proofs is to stay on one side. But another strategy is if you get stuck on one side, stop, go to the other side and work a little bit on that side. And as long as the bottom line on both sides are the same, you've completed the proof. Now, the other thing that we want to make sure we do not do is to go back to the definitions in terms of X, Y, and R. We did that in the very beginning to prove the fundamental identities because there was no way else to prove them. They were so fundamental and basic, we had to use the definitions. But now we're using those fundamental identities in conjunction with algebra to solve these, okay? So there's two ways to do that one problem. Both of them are a little bit different. The one on the left, instead of factoring, we actually expanded. And on the right, we factored. Both of them are viable, right? It just kind of matters on how you proceed. Do you start with an algebraic substitution, sine to the fourth with sine squared squared, or do you start with the trigonometric substitution? Go from there. All right. So it's not necessarily going to alternate substitute with the trig identity, algebra, substitute, algebra. It's just any combination of those two in any order. All right. Does anyone see a third way or a different way to do that one? We can entertain that idea if you'd like. I got it. What if we had started on the right-hand side instead of the left-hand side? Well, let me just show you. Sometimes you're like, I can build a house. I have the knowledge. I have the expertise. I have the time. I don't have to be a home wrecker. I could be a home builder. So if you did start on the right-hand side, what would be your first step? Well, it's real easy because if you're going to start on the right-hand side, all you got to do is go to the other side that you've already done and just imagine doing it in reverse. So what would you do first? Well, you would have to realize that, hey, I'm going to add a clever form of 0. I'm going to leave 1 minus cosine squared, the 2 cosine squared, but I'm going to add a clever form of 0, plus cosine to the fourth of x minus cosine to the fourth of x. And you're like, how would you know to add a clever form of 0? And how would you know to add that version of it? Well, that's where your knowledge and expertise comes in. And then you would use the associative property of addition, and you would factor that as 1 minus cosine squared of x, quantity squared, and then you would bring that around. You see what I'm saying? And then you would use Papa PID. So basically, starting on the other side would be basically doing either one of the two ways we did it on the left, just doing it in reverse. Okay, I'm not going to finish that. But what's cool is once you create a proof, you've actually created this logical loop of equivalent steps. And you can jump in on any line and go clockwise or counterclockwise. And every line is equivalent to the one above or below. Okay. There you go. All right. Any other comments or questions on example 1? When we ultimately test on this next week, you'll have 3 sections. Your first section will be using just these fundamental identities. Well, since we're not going to do the next set of identities, I don't think, I mean, unless Miss Lincoln forces me, you'll have a safety net. Like I'll say, do 6 out of 7. You'll have 2 parts if we don't go on to the next section. Part 1 will be like do 6 of the 7. So if you can't do one of them, you know, you could try it. And if you get them all right, you can get bonus. Or you can attempt all of them, and I'll grade the 6 most correct out of the 7. And then the second part will be solving equations, and I'll have you solve like 4 out of 5. Okay. So in each section, you'll have this little safety net. Bless you. Okay. So here's what we gleaned out of that first one, right? Start on the more challenging side with more information. Try factoring. What are some special products, common factors, difference of squares, perfect squares, trinomials, so on and so forth. Okay. All right, let's do example 2. Prove the following identity. Draw a line down the middle. All right, that's your first step. The next step is to decide which side to start on. Which side looks more complicated or has more information?
The right side.
Why the right side? There's no wrong answer. What, just why the right side, would you say?
I'd say because of it. I'd say because of it being multiplication and not addition.
Okay, stop right there. I like it. Multiplication is higher on the operation ladder than addition, right? So you could definitely start on the right for that reason. Just like having a higher power, like we did in the previous one, is like a denser nucleus. You have more information. in terms of the trig functions, neither side is in terms of sine or cosine. So it's just kind of a really a subjective thing there. Now, I would recommend starting on the left side. Not that the right side's wrong, Brady, but here's why I would recommend starting on the left side, and this goes to a strategy. It's easier to get two terms into a single term by getting a common denominator than it is to split up a single term into two terms. Okay, to decompose a single fraction into partial fractions, it's not always easy, but it is a lot easier to take two things that are fractions and add them by getting a common denominator. Now you're saying, what fractions? I don't see fractions at all. Well, that would be kind of my first step. I'm going to start on the left because it's two terms, and the right side is now my target. I'm going to create denominators by putting them in terms of sine and cosine. So that's another strategy that you can use at any time. If it's not already in terms of sine and cosine, do so. So here we go. Using the ratio identity, tangent is sine x over cosine x. And then using the ratio identity again, I get cosine x over sine of x. There you go. All right, now I need to get a common denominator. And the common denominator is just the product cosine times sine. You can do the crisscross applesauce butterfly multiply. I'm fine with that. So that works well when your common denominator is their product, which means they're co-prime. You just have to start in the top left. So top left times bottom right. What's sine times sine? Sine squared. Then you take the middle sign, which is plus, and then you take the other product, which is bottom left times top right. What's cosine times cosine? Cosine squared. And then it's all over the product of the two, which is cosine x times sine of x. Okay, so that's your first step. You just have to start in the top left. Now, when you're doing a proof, remember, I need to be able to see your steps. So that highlighting stuff, I wouldn't necessarily do. I just did that for illustrative purposes. Now, if you don't want to do the crisscross applesauce, which is perfectly legal, the other way to do it is to actually show that you're getting a common denominator. It's a bit more writing, but it works, right? To do that, you multiply each fraction by a clever form of 1, and it's the other factor's denominator. So for this one, I need cosine over cosine. And then for the first one, I need to multiply by sine over sine. So this is the correct way to do it. Multiplying by 1 doesn't change the value. And now I have my common denominator of sine times cosine. And now I can multiply straight across. So this would be the optional step. The key is not to mess up and to keep every line equivalent to the line above or below it. Optional. All right. Now we reassess. Anything good happening here? Hey, there's a 1 on top. That's Papa Pid. Very good. So on the next line, I'm going to call it 1 over cosine x sine of x. Okay, now remember, take a look at your target on the other side periodically. That's what we're trying to hit. They say if you don't know where you're going, any road will get you there. Ha 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 ha. We know where we're going. We got to get to the product secant times cosecant. How can we proceed on the left then? Well, I see how to go, but let's say hypothetically that you're stuck in, right, on the left. You're not quite sure how to do it. Remember, at any time, the ultimate get unstuck strategy is to put everything in terms of sine and cosine if it's not already so. So let's jump to the right side. We're going to abandon the left and we jump to the right side. We can't like add 5 to both sides. We can't subtract secant and cosecant from both sides, but we can work on it independently. Secant is 1 over cosine and cosecant is 1 over sine. And now, because they're fractions that are multiplied, do we need a common denominator to multiply fractions? No. To multiply fractions, we just multiply straight across. What's 1 times 1? 1. What's cosine times sine? Cosine times sine. Does the left side look exactly like the right side? Yes. So we're done. Now, let me show you this. What if, hypothetically, on the right side, I had 1 over sine times cosine? Does the left side look like the right side now?
Not exactly.
Not exactly. So you couldn't stop there. You wouldn't get full credit because the commutative property would be the reason why you'd want to commute the factors in the bottom. So don't stop until you get the left side and the right side to look exactly like each other,
I kind of.
but for the position, but for the color, but for the writing. And so now the left side equals the right side. And so now we're done. Now I'm not going to celebrate with my signature QED because this is not the preferred way to do it, although you wouldn't lose points for this, right? The preferred way to do it is if you start on one side, stay on that one side. Now, having said that, since we did jump to the other side and it gave us some insight, can we retreat back to the other side and complete it on one side now? Yeah, because remember, doing it on the right side gives you your template for what you should now do in reverse. What should be my next step on the left if I want to stay on that side? Break it up. Yeah, now this would be breaking it up into, it's still a single term. Splitting up factors is a lot easier than splitting up terms. And now 1 over cosine is secant and 1 over sine is cosecant. So if you'd like, you can do that on the other side, and then you can come back over here and erase that work. And now you've got it looking prettier. And instead of saying done, you can now say, hooray. Okay. But do you have to do that? Will I count off if you don't do that? If you actually work on the other side as well? That's fine. Now, don't work on the other side and then like get to a dead end and then jump back to the other side and then have this equal, like don't come over here and say like cosecant of pi halves minus x times secant of pi halves minus x, and then say, oh, that's not going to work, and then come down here and then now get this to equal what was originally over there, because would you get full credit for that? No, because now the bottom lines don't look the same. So if you don't want to erase, just draw a line through it and then I don't see it. Okay, it's easier than erasing. That's right. Okay. Is there another way to do that problem? Probably so. Probably so. Am I going to do it that way? Probably not. I want to look at more examples. All right, let's glean the juicy morsels. When all else fails, get everything in terms of sine and cosine, and combine terms by getting a common denominator. So starting on the side that has more terms rather than more factors. Okay, example 3, I'm going to let you jump in and give that one the first try on your own. There is no wrong answer. There's just a less efficient way to do it. So long as you're doing legitimate math and you're making legitimate substitutions with identities, some routes are just more scenic and you might have to know when to abandon a route rather than be bullheaded and proceed. So take a couple of minutes to try this on your own and I'll take attendance. Be fearless. You got to be fearless. I'm starting on the left side simply because it's 2 terms once again, yes? And the right side is 1 term. I need to get a common denominator. It's their product. And oh, by the way, those are conjugates. So crisscross applesauce, right? 1 times that is just 1 times that. I'm not going to distribute right away. I'm frozen. Dang it. All right. Plus, and then the other diagonal, that times 1. And again, I'm not going to distribute it, whether it's a 1 or a 3 or anything. I'm just going to do that first. And then all over the product, I'm not going to expand it. You don't want to do too many steps in one, otherwise you may lose your reader, right? Which will be me. The process is the product. When in doubt, do not leave it out. Now that I have a single factor, hey, do those divide out? Do those divide out? No, they're terms in the top. So here's what we do. We look at the other side and we're like, okay, we are making progress. We have 1 term. Now, remember, we talked about this in 6.1. You do not want to distribute the bottom. Even though they're conjugates, you want to hold off because it's completely factored. And remember, we can only divide out common factors. So the top, which is only partially factored, you do want to distribute. Now, it may turn out later down the line that we do want to actually expand the bottom, but for right now, we'll leave it factored. So distribute the 1 on the top, and you get secant x plus 1 plus secant of x minus 1, and we'll just leave it over the product of these two conjugates. All right, anything good happening in the top? What's happening with the ones? Yeah, the ones cancel, and secant plus secant is 2 secant. So, hey, look, the right side, I wanted a 2, didn't I? I got my 2. I'm not messing with the 2 anymore. No sirree, Bob. Okay, now I look at the denominator. Do I want to leave it factored now in the bottom? The whole purpose of leaving it completely factored is because something may divide out. Do these secants divide out or anything like that? No. Now, because nothing divides out, now I think I will expand the bottom, but I held off, right? At this point, I don't think I would even put it in terms of sine and cosine. It wouldn't be incorrect, but notice the right side's not in terms of sine and cosine either. So I'm going to try and hold off on that until I really get your stuck in. Okay, so now I'm going to distribute the bottom. Those are conjugates, so I get a difference of squares. Secant squared of x minus 1. And now we're like, oh, okay. Anytime you have a squared trig function, especially in the presence of the number 1, you should be thinking with PIDs, right? And what is another name for secant squared minus 1? It is tangent squared. Good, good. I'm not even going to show you why or write it off to the side, but you know your identities. 1 plus tangent squared is secant squared. So if you solve that, secant squared minus 1 is tangent squared. Now, are we making progress? Look at the right-hand side. Yeah. Do you want to keep going on the left-hand side or not? I'm going to hold off, okay? I'm going to jump. Not only am I running out of room on the left, but I'm running out of ideas short of putting it in terms of sine and cosine. So here's what I'm going to do. Notice that I want to pick up 2 tangent squared factors in the bottom. Well, I have a cotangent squared factor in the top, don't I? So I'm going to write that cotangent as 1 over tangent. That gives me a tangent in the bottom. Now the cosecant, man, I really would like to call that something in terms of tangent, but I don't know what it is in terms of tangent. Do you? Cosecant is not sine. Cosecant is 1 over sine. Is that what you mean? Yeah, okay. So let's call that 1 over sine. Okay, now my target is this. I'm trying to call it 2 secant tangent squared. Oh my gosh. Is that going to help me? What do I do on the right-hand side now? I basically need to show that 1 over sine is the same as secant over tangent. I need to pick up another secant over tangent, don't I? I do. How am I going to do that? No ideas? Okay. How about this? Can I multiply by a clever form of 1? Yeah. How about let's do this? I need to pick up another tangent factor in the bottom. Would you agree? Yeah. So sometimes we can create what we need as long as we do it legally. What if I multiplied by tangent of x over tangent of x? Would that be legal on the right-hand side? Yeah, because that's 1. So let's do this. Let's group this 2 and this tangent and that tangent together. Okay. And I'm going to call that, I'm going to group those together. This is the associative property of multiplication, the 2 tangent times tangent. So I'm going to call that 2 over tangent squared of x. Okay. So now all I have really left to show is the following. I need to show what's left, which is a tangent of x over sine of x. I need to show that that's equal to a secant of x. You think I could do that? I hope so. Here's how I'm going to do it. I'm going to put everything in terms of sine and cosine. I'm going to keep the 1 over sine of x. That's good. And then I'm going to call the tangent in the numerator sine of x over cosine of x. And what happens with one of the sine factors? They divide out, and I'm left with 1 over cosine. What's another name for 1 over cosine? Secant. So now I get 2 secant of x all over tangent squared of x. Does the left side look like the right side? Yes. So now I'm done, and I'm going to breathe a sigh of relief. Phew, right? Like you're wiping your brow. So there you go. That one was pretty interesting. If you get stuck on one side, go to the other side. What's another strategy? Create what you need. Create what you need, but do it legally, right? I needed a tangent at the bottom, so I multiplied by tangent over tangent. The associative property of multiplication would be another strategy. Group the factors together that you need, that you already have in place, right? When you compare it to the other side, and then work on the other factors, and you kind of reduce the proof down to a smaller proof. In other words, right there at the end, I reduced the proof down to showing that secant of x was equivalent to 1 over sine of x times tangent of x, right? Keep inventory of what you have on one side and what you're trying to get on the other. All right. Now, the little bullet point here said to eliminate complex fractions. We didn't even have complex fractions, did we? No. So I guess there's another way to do it. Let's see if there's another way to do it. If I would have started on the left-hand side, let's just start on the left-hand side. I could have had 1 over secant of x minus 1 plus 1 over secant of x plus 1. Some people are like, you know what? I'm not going to wait until the end to put everything in terms of sine and cosine. I'm going to do it from the get-go. So that would be 1 over cosine minus 1 plus 1 over cosine minus or plus 1. Now, in each of these, I can't do state change flip because I don't have a single fraction in the bottom, but I can multiply by cosine over cosine, which is LCM over LCM, or as we called it, lickem over lickem, because I have a common denominator of cosine. Now, when I multiply in the top, I get cosine of x, and in the bottom, when I distribute, I get 1 minus cosine of x. Same thing over here. I get cosine of x, and when I distribute in the bottom, I get 1 plus cosine of x. So really all I've done is I've taken the left side, or got rid of the secant, and put it in terms of cosine. How would I proceed from there? Well, I would probably get a common denominator now by doing crisscross applesauce. But now, since the left side is in terms of sine and cosine, I would probably jump over to the other side and put it in terms of sine and cosine. 2 times cosine x over sine of x times 1 over sine of x. And that gives me 2 cosine of x over sine squared of x. And I would stop there. That looks like a pretty good simplified version. And then over here, if I crisscross applesauce, that's cosine of x plus cosine squared when I distribute, plus cosine of x minus cosine squared if I distribute, all over 1 minus cosine squared if I expand. Well, look what happens. These cancel, and I'm left with 2 cosine of x. And then in the bottom, that's sine squared by Papa Pid. Does that side now look like this side? Here's the left side doing another way. Here's the right side doing another way. Yeah. So which side is more, which version is more correct? The purple one in the main frame or the blue on the outside? They're the same, right? It's just a different way to do it. So this one just puts it in terms of cosine and sine, which maybe you're more comfortable. The other one is keeping it in terms of secant and cosecant. So as long as you are fearless, you don't just sit there and stare at it, you do something. You do something. As long as it's a legal math move, like lick'em over lick'em, multiplying by clever forms of 1, creating what you need, and you're doing legitimate substitutions with the identities that you have memorized, you can keep chipping away at it with the other side as your target. And in the end, when the bottom sides are equal, even if you didn't stay on one side, you're Brooks and Dunn, just like we are today. All right. Try the worksheet. The worksheet I put in Canvas, practice as soon as you can. Start reinforcing these ideas, these strategies. They're all a little bit different, but you have the ability to do all of them at this point. Okay. I'll see y'all tomorrow. Hopefully, maybe, unless you're not here, right? At which point we'll be forging on in 6.2. So thank y'all today. Bye.